Okay, so today I'm gonna go over the homework 12 um, R, R tutorial or R session. Mm, today we will go over the some of the some of things that you already know, and then such as ln, the linear model, and how to choose the variables in your model. So first of all, usually I start the R by doing the cleansing the data and setting the working directory. Okay, and in the working directory, you can go to here, go to working directory. Okay, so you have the retail sales CSV file. So you read the CSV file as data, and then I'm just going to open up the data file by view data. So you see these four variables of sales distance, square feet, and swimming pool. For this session, we are not going to use the swimming pool here. So um, so we're just gonna look at these three variables: sales distance and square feet. So the problem here, or the question here, is to come up with a linear model which predicts the sales in terms of distance and the square feet. Okay, so we start forming the regression model um, by ln function. This is our y variable, the response variable, and then the distance is the predictor, and we are using the data as our data. This command and this command are the same. So instead of specifying this way, I'm specifying the y variable as data $sales and the x variable as data $distance. Okay, so I'm going to run this, and then I'm going to run the summary of our model. Okay, so all right, okay. So if you look at our summary of our model, we see this part. So this is the value of our intercept, and this is our slope. So we have to look at the t-value, or t-statistic here. Since t-statistic is high, which gives us that p-value very small, we can trust this value. So here the null hypothesis is that the slope, or the parameter of the here is 0. So since we have the p-value smaller than usually 0.05, we reject our null hypothesis that the slope is 0. So we keep this number in our model. Another thing you should look at is the multiple r squared. So r squared is here is 0.55. Sometimes it's high. Sometimes we can interpret this as really high, or sometimes it's kind of really small. But just bear in mind, just keep this number, keep this r squared in mind, so that the r squares value tell us how much y, the sales, is explained by the distance. Okay. So we have our model. By running the regression model, we know that our regression model should have this form. Okay. So here, the y, the response variable, is sales, and a, the the parameter of our slope, or the slope, is this number, and then b is the intercept. Okay. So also we can plot our x and y value. Zoom in. Yeah, you can kind of see that you have this linear trend graph, but then these data points are not really close to the linear slope that we can draw. They're spread it out, okay, which tell us that the r square is not really close to 1, but rather close to 0.5 or half. So we already have this model. Okay, so what I'm trying to do here is I'm trying to add the second x variable. Okay, so it's the same. This is our response variable, and this is the first predictor, and this is our second predictor. Okay, so if you write this is same as a1 times x of 1 2 times x of 2 plus our intercept. Okay, let's run this one first, and then let's see the summary of our regression model. Okay, so we can look at this result. So we can see is that the first of all, r square increased when we add an extra variable to predict the y variable. The r square always increases, which means by adding additional variable, we can explain the y variable more. Right? So the second thing you should look at is the t value or t statistics of each parameter. So for square feet, we have relatively large t statistic, and then which means that we have very small p value. So since we have a small p value, we can reject our null hypothesis that the slope is 0. So in other words, we can say that slope is not 0. So we can trust, or we can trust this number. The second variable for distance, we have t statistic very relatively small or close to 0, which give us the p value high, right? So what does this mean? Since we have big p value, bigger than 0.05, we cannot reject our null hypothesis that the slope of distance is 0. Since we cannot reject our null hypothesis, we should assume that the slope of the distance is 0, right? So if I write it this way, this means that distance, the sales price is equals to 283.47 times the square feet plus or minus 90760 times distance plus 4718. Okay, but then as I mentioned, we should not reject our null hypothesis, so this should become 0, which means that we can just delete this part. Okay? Also, since we have an extra variable that we do not need, we should perform another regression with this variable only. Okay, So that's what I did here. So then we run the regression again with the square feet only. Okay. The regression, so sales is y variable and square feet is x variable with our data. I run this, and then let's see the summary. Okay, so in the previous model, when we have the two variables, the r square was 0.7327. Now we have one variable, but then r square is very close to what we had, 0.7. Now we have 0.7323, and adjusted r square is 0.7272. And then earlier we have adjusted r square 0.7224, which is smaller than what we have in our third model. Let's look at our result here. We see that our p-value is very small, so we can reject our null hypothesis that the slope is 0. So we can keep this number, right? So what does this suggest? So in order to predict the sales, we should use this 271.70 times the square feet plus and this intercept here, 14355. All right. So if we have a 10,000 square feet house, we can say that the sales price for 10,000 square feet house is about 2.9 million. Okay. If we are to predict a sales value of a house with 5,000 square feet, then we can just do this way and run it and output the sales. Then we have about 0.57 million. Okay. So, this is how we predict the y variable when we are given the parameters, the slope, and the intercept. Okay. Another thing which is important is to check the regression conditions. First of all, it is also better. It's a good idea to do the regression checking first before you end up with before you make any conclusion. So we are going to find the residuals of our model, the third model, like this, and then we are going to draw the QQ plot of our residuals, and we are going to add the line to our QQ plot, and we're going to zoom in this plot. Okay, so residuals are lined up to this line, which we can say that the distribution of the residual is normal, right? Which tells us that the one of the regression condition, which is normality, is satisfied. The another assumption is the linearity and the equal spread. We can figure that out with by plotting the residuals and the x variable. Okay, and then I'm going to add the trend line also. Okay, So we can see that there is no such pattern in our residuals. So we can say that um, the model has uh, the equal spread. Um, the equal spread condition is met with this model, and we also do not see any patterns like this one or any any regular pattern that we can decide that whether this is non-linear. So since we can see that it's pretty linear, or there's no such shape that we can say that there is any um, trend that we can say that this our regression model is linear. Okay, so this is, I think I already explained how to make the prediction of um, how to make the prediction when we are given an x variable. Right? All right. Thank you for listening. This is the end of the session.